Okay. Welcome to our Thursday system design session. And in today's session, I would like to. Today's topic is still about the web crawler, and I think this is our topic, and you may know this before, and we talked about it before. And this time, we're going to talk about the web crawler with unreliable workers. And previously in last session, we talked about the basic design, and you can see from the drawing mode, there's a big picture of that. And there is some unresolved problem, which is the how to refresh the pages. And another thing is indexing, how we index the pages so we can search. So these are two things left over. And yeah, as usual, I would like call for the volunteer as a presenter, design the system, and the other guys can jump in and help. So is anyone of you want to try this out? Even though we have only 3 of you. And,
Is this a continuation from the last week?
yeah, this is.
I was not there.
Okay. Do you want to try this? So we can, if you open the drawing mode, I can give you some overview of the previous session. Because I don't really know that which of you were here last time. So you can see you need to zoom out the drawing mode a little bit. So we have basically we have a big loop that we have a seeder that get the database, gets some seeding, some initial website to the system, and it will assign the workers to different workers. And then there is a content collector collect the result from these workers and put them into the database, and also put the metadata into another database, which contain the timestamp and maybe other URLs and something. Then there is some checker that read the data from the metadata and will decide which one to put back to the seeder. So basically, which one we want to refresh, and yeah, I think that's the idea, basic idea. So yeah, I think the key thing we want to design here, that we want to design a kind of queue that will tell us that when it will accept the URL and into the system, and that will, yeah, periodically it will check if this URL is ongoing or not, and also whether we are going to refresh this URL or not, such a thing. So yeah, this is a very the queue, the basic idea of this queue.
Okay.
Do you have question? Or maybe you can have some better idea.
So, was there any drawing code last time?
Uh, join. Yeah, you go to the coder pad, and if you go to the
Oh,
join
in the
mode,
in the coder pad itself. Got
yeah,
it. Got it.
yeah,
Got
it will go. It will show a window, and if you go to the
it. Mm-hmm.
top right corner, there is
Okay. Okay. I think,
yeah.
yeah. I think before that we were using that AWS apps, so that's why I
Mm,
got confused.
uh,
Like AW apps something.
yeah, because this time we can use a single app. In fact, I can.
Looks like already a lot of design happened. So,
Yeah, there is a lot of
so
join.
if Ankita or Momen was there last time, I think they can also contribute. We are just four people, so if they're
Hey,
not,
I was not there too last
Okay.
time.
so
Yeah.
Same here. I was not there last time. I couldn't make it
Can
last
you
time.
share the link of the code pad?
Sure. Let me put this um in the chat. Okay, I see you. Can you see that? Actually, I can see all of you in the coder pad.
hmm. So
Yeah, because actually, oh,
as
go
none
ahead.
of us was there last time, either we can pick up a new problem or
Hmm,
just keep on brainstorming on this. I don't have context like what was discussed
hmm,
last time. So
okay. Yeah,
yeah.
actually, I can remember very well. Um, but the basic idea is that this we have the seeder and we have some workers. I think at this time probably yeah, because my idea is this one is for someone from someone else, and I feel like if we want to design a worker, um, the worker need to take more responsibility. That they may need to decide what to download. They can download one page and parse it and uh, create multiple sub pages. Sorry, not sub pages. It try to parse out some more URLs from this page and fetch multiple round so that they can get many pages and send it to the content collector. Otherwise, you download the page and send to the content collector. There's no benefit of that because the content collector may download the thing directly. So I feel like the workers need to do some work rather than simply the content forwarder. Sorry.
So how do we ensure? Obviously, right? There are if you start in a root URL and then basically you download that page and then you parse. whichever worker downloads that page, it parses, right? There can be more URLs, right?
Yeah.
So this URL list keeps growing, right? So how do we ensure that these URLs are distributed across all the worker nodes uniformly? Like it's not meaning like it's not just like one, like few workers have a lot of load versus few workers don't have load, right? Like that. How do we uniformly distribute nodes uh, load across all the workers? That's one element. Second element is how do we ensure we don't download the same page again and again, right?
So I feel like it's very hard to avoid the we can have the controller here is a seeder that distribute to the URL to different nodes. So at this step, I feel like we can evenly distribute the work. But once we pass the URL to each workers may pass the URL from this URL. Basically, you download the page and parse the content, and it generate more URLs. At this moment, it doesn't know what are other nodes work. So it will try its best to um, get multiple layers of URL and give it either to the content collector or maybe to the seeder or some controller. So then the controller may receive this URL from different workers, and it may notice that some of them may be updated recently. So it may decide not to go deeper. And yeah, so this is something that the controller receive the URL from different workers at different times. So it will decide that if there's URL updated recently, it may decide that, okay, I don't need to work on this for a while, and until maybe later after a couple of days. So in this way, we can reduce the unnecessary load. What do you think?
So I think let's quickly go through this. So in this high level design you put together previously, right? So there are different nodes. I'm assuming the N1, N2, N3 are they all the worker nodes that are doing the crawling? What is the first box?
First box is seeder.
The first root URL.
Which one?
This one. 1 second. Let me.
Yeah, you can draw for in the.
Yeah. This one, the seeder.
Seeder.
Yeah.
This one I feel like this. Yeah, last time the presenter said that this can be the controller that pick up the initial. Actually, it will get the URL from different sources and distribute the work to the different workers. So let me draw here.
And N1, N2, N3, they are the nodes, worker nodes, right?
Yeah, that's right.
And then I see there is URL downloaded. There is, and there is one more box here. Content collector. Is it content collector?
Content. Yeah, here. Right.
So is that the downloaded content, the page content?
Yeah, that is a controller to receive the downloaded content from the worker.
And what does it do with the content once the page is downloaded?
It will put in the one database.
And that's the content database. All the web pages go there. I see two databases. There's a one on the top, one on the bottom, right?
Yeah, this is the top one is content. And the lower one is metadata.
Metadata. So what constitutes metadata in this example?
The timestamp to expire for this URL. I feel.
Okay.
Yeah, the URL and the some timestamp. I think we need to go deeper about those two things, because these are related to how we want to refresh the page.
Right.
And
So I feel like I think there's some critical elements are missing here. So one thing is we need to maintain a list of all the URLs yet to be. So we need two kind of lists, right? One list URLs that are yet to be crawled, and other URLs that are already crawled.
yeah, right.
Right.
Yeah.
So the once we keep the URLs that yet to be crawled in a list, right, and that can be distributed. The worker nodes can pick up from there.
Mm-hmm.
And the reason we need to list up that's already crawled, we don't need to probably store all the URLs that are already crawled. We can probably store hashes that just to make sure that you're not, if you're crawling one snap at a time, right? So without not to download repeatedly, we can check that hash index and see is that downloaded. So we don't because the same page can come up again and again, correct? In the subsequent crawlings. So we can use already downloaded URL hash, and and we know if the hash present there, it means it's already downloaded, right? So we can skip that. So we need that one. We need second one, and the yet to be downloaded one is a list where from where the workers pick up to crawl. That second list, and that's a second storage, and the third one is obviously the content where the actual page goes, right? Actual web content goes.
Yeah. Let's focus on the missing part that here. Let me put here. We can have something here. The first time I'm using this. That's not very well. So, but let's try to have something here. So if there is a database contain the thing, at least we have the URL. And what we can do is that we can virtually have the content, even though the content may be stored somewhere else. And URL can use as a key, and there could be one expire time. And this expire time, initially it can be, so initially we have the seed URL and we have no content, and expire time could be current or sometime before. So anyway, each time so initially when we go through this table, we will know that this URL is expired, and we need to update this thing into with some worker, and there could be some status. It's going out, and that status can be something like it's running, or it could be running or ready, the two state. Oh, it's going out. So I think in this way, this table will serve different purpose. So it will tell that which URL need to be updated by have the expired time, and we have the expire time, and the status can be ready or running. So if you the next time when this when the controller goes through this database, if you see that yeah, I think actually if we have only one controller, the controller knows that which content is being downloaded. So in this way, we do not really need a status because that can be looked up into some internal database. And then the controller will periodically check the expire time, and if the expire if this entry is expired, the controller will need to put this URL into some worker if there's worker available. And then it will internally mark this entry is busy, so it won't go through the same entry the next time when it goes through the database. So that means that there could be only one controller and multiple followers. At least there should be one leader controller that manage which URL is going to be ready or which URL is running by some worker. So yeah, this is my thinking about handling the expire, refresh the refreshed content thing. What do you guys think about this? Oh, we have the chat. Okay. Yeah, this is my thinking about the design. What do you guys think? What do you guys think that we can improve?
You are basically storing a list of all the URLs, and basically it's kind of this is a URL store, right? It also contains the actual content. And
That can be a pointer to I put it here. The content here means that there's a pointer pointing to the somewhere. That content itself can be in the object storage or file system anywhere.
okay.
So we are going to store the content in a separate store.
Yeah, somewhere that can hold the content.
Okay. But this content. So here we are not discussing about. We're just talking about how to get the content, right? Not about the indexing. What we'll do after the crawling, correct?
Yeah, this is another topic I want to say, the
Okay.
indexing thing. Because if we go
Yeah.
further, I think the content itself is not really necessary, but we need to
Exactly.
put index.
Yeah, I mean, what you'll do with the crawling, right? After that, the whole purpose is to search.
Yeah, you are right. I think this is something we didn't know initially, and later I find that we don't really need the content.
Okay. So I just joined a little bit late, Hiran. Is the algorithm you already discussed, like how it is going to be, how it is going to be followed, the core algorithm? Oh, okay, got it.
Okay. Yeah,
Okay,
this is the previous one is from someone else, and I feel like we need to redefine. We need to make the metadata and the content database clearer and we need to handle the refreshing. So here, I think we need to make. See, in this case, we already know that we are going to index the content. So let's put this way. This is real index, even though that the index itself can also be somewhere else. But let's put it here. So
Yeah.
when we have the URL, we will have the index, and the URL will also create multiple links, and that links will be the additional entries in this. Oh, that will be part of the this database. There may be some URL 2 or 3, and they may have the index. They may not have the index, and they have the expired time. So if there is a if the worker returns some URL 2 or 3 back to the controller, the controller will look up into the table. If there is such if there's such an entry in the database that with expired time that is some time in the future, then we consider that this URL is handled properly previously by some worker. So we don't have to worry about that. So we will ignore we will skip this URL. But if it does not, this URL2 does not exist in the database, or the expired time is sometime before, that means that this URL is new or need to be refreshed. So it will be re-entered into the system, treated like a new one. So in this way, we can refresh. Yeah.
The expiration time is what? Like, who is going to calculate the expiration time?
Expired time will be so. So let's say this way: if there is a, so if this content is entered initially or is updated, then we will calculate. We will calculate the expired time. That could be the time stamp will be the current time of some controller, even though the time may not be very accurate, but roughly it's okay. So maybe now it's 12:33 p.m. and we can set the expired time to be 6 p.m., 7 p.m. in the future.
Okay. So here we are not really comparing the content, right? Let's say that in 2 hours, the content may not be changed on the website, but still we are going to crawling, right?
Yeah, we don't have to compare the content.
Okay.
I don't think it's necessary.
Okay.
Yeah, I think we may, if we are periodically crawling, right? Assuming like each web page we crawl, let's say, for example, once a week, right? So then probably what we could do is you could have a URL list stored, and then in basically in kind of in an ordered list, right? In a sorted list by the expiry timestamp.
Yeah.
So every worker picks up from the head the URL. Once it is crawled, they go and append at the tail, right? Remove from the head, append at the tail. It's like a queue. Every time you're removing from head, you crawl, store the content, you append at the tail. Then, but
yeah, there's the
right.
tail here. It probably means the expired time.
Correct. You open the tail, but you only schedule like it's basically it's a list sorted by time order. So you only like you remove from the head only after time expiry, right? So if it is sorted by the time, so after time expiry you remove from the head. and then you start another timer with the timeout that's corresponding to next element, right? So it's that's how typical timers are implemented. So that kind of logic you could use. You remove from head of a timer expiry, because the head is the element in the head is the one supposed to expire at the earliest, right?
Yeah.
So, and then once that time elapsed, you go and remove it, crawl it, append at the and then you add one in, like, let's say 1 week, right? You add that 1 week time to that list and append at the tail.
Yeah.
So you keep on doing that basically.
Then here we don't really have the queue, but this is this behaves like a queue, but not really queue. Because
So what data structure is it? This one? This URL, we are maintaining, how we are keeping track of this one? Is this a database? No, right?
Yeah, this here is a database.
Database, yeah.
Okay.
Or something similar to database.
Right. Yeah, so I think once the website is downloaded, probably you could put that the content, the URL, and the time at which the page was fetched, things like that in the database, right? And every time you download, you update this corresponding row, and then you could use this database to generate the secondary index on the web content, right? Yeah, so so that's another index. So you have a database of all the download content, and you have the actual like the search index is stored separately.
Yeah, let me just, maybe I can write the loop somewhere in the below this thing. So my thinking that in this way, the loop, the system will be like we have the controller, and virtually this is a controller, and it will still connect to several workers. Multiple workers, and the workers will communicate. Yeah, this communication will be the two-way communication that the controller will assign the work based on this database, and yeah, the controller will assign the worker. The worker will return the index data and the sub URLs. And if we think necessary, we can have a second degree URL and indexes, so we can keep the worker busier, because communication may also expensive if we have them not reliable.
Yeah. So I think so we could basically we could treat all the workers basically kind of a cluster, right? So one thing we could do is, I think the control, I'm not sure if central controlling is going to, maybe that could be a bottleneck. So one way to do this is basically assuming all the URLs, right? If you hash them, it's basically using some kind of constraint hashing concept. You could distribute hash space, right, among all the nodes, right, in the cluster, and each node responsible for certain range of hashes. So that way, whichever, let's say one worker, let's say, crawls URL 1, it downloads, parses, stores it. Then once it parses the URL, it finds there are, like, let's say, like 10 other URLs, right? It calculates the hashes of all those URLs, and then based on the hash, right? So assuming each node maintains that complete hash map, which hash belongs to what node, then it could just basically send that request to other nodes responsible for that hash. So that way, each node responsible for a certain hash space, they will be responsible for crawling, a specific set of URLs. And that uniformly distributes the load, because hash is supposed to be like random uniform distribution. That's
Maybe
one
you
advantage.
maybe you can write into this code pack. I'm not familiar with this thing. That I was talking about distributing hash table or something, because I heard about that from BitTorrent, but I don't really understand what is that.
Yeah. So basically, it's so
Let
let
me
me
stop
let me
share and
write
you may
this.
share. Yeah, that's just something I really want to learn.
Okay. You want me to? So where do I draw this coder pad?
Yeah,
Can you?
yeah, if you go to CodePad, there's the join mode, and you click on that. I think I feel like some of you may not have that here. I put them in the Zoom chat again.
Yeah, drawing mode. Yeah, I saw that. I get the drawing mode.
Yeah, if you make it bigger, and then you should
Yeah.
be able to. Yeah.
Yeah. So let me draw here. So assume. So basically, I think this is this basically concept came from the card protocol, right? That's what.
Okay.
Are you not? I'm not seeing your screen actually.
Yeah, I think you
I'm.
can share the screen and
You don't see what I'm writing here?
I can see that, but
You
I'm
can
not
see, right?
sure. Yeah, I'm not sure others guys can see or not. So can you
Yeah,
share it?
actually in the recording it won't come.
Yeah.
Let me
So
go there then. Okay. Yeah, I think that's fine. I
yeah,
can
just
go to
you
URL.
select drawing mode, right? I
Yeah.
think you should see what I'm typing, right? So basically assume, right? You have a number of nodes, right? So assume that we are maintaining with those nodes, right? Kind of a ring topology. Okay, ring topology, right?
Okay.
So when you have n nodes, right, you can arrange them in different kind of topology. It can be with a central control approach you explained. That's what we call a star topology, right? Center, the master, the controller in the center, and it is the one communicating with all other nodes, right? So that's a ring topology. That's a star topology. So this is ring topology. So so let's say so all the URL when you hash, okay? Let's say all the hash the generates just for simplicity, let's say it hash you finally you get from URL a 4-byte, okay, 4-byte kind of value, right?
Okay.
So what you could do is in this 4-byte hash, so it starts from 0 0 0 0 0 0 to f f f, correct? Like 8 f's, right? So in this entire hash space can be split into, let's say node 1 gets from 0 0 0 to like let's say 1 1 1 1 1 1, right? Second one gets from 1 1 1 1 to 2 2 2 2 2. Okay, so this hash range is kind of distributed among
This
all
is
these nodes.
consistent hashing. Is it
Yeah,
correct?
exactly. Use the same concept here. So you
Okay.
hash the URL. Let's say this node, let's say downloads, let's say www.google.com, right? Or something like reddit.com. Okay, once it downloads, it parses within and then actual content itself, it can store in the database. Then once it parses the content and then finds more URLs, right? So it basically finds hash of the URL, and it know and so assume, so let's assume like they use some protocol like card to maintain the topology. Okay, there are protocols to keep the track of the topology, and so that each node knows what other node is responsible for. So once it finds the hash, and then it knows this node is responsible for that, right? So it through this protocol it sends that, okay, this is a new URL you need to crawl. So it goes all the way to this node. 1 2 3 4, it comes to node 4, right? And now node 4 is going to crawl that. So this way now all the URLs are strictly distributed to nodes purely based on the hash. So that way you can guarantee that you uniformly distributing all the request URLs across all the nodes.
Okay. So
and another advantage with this approach is, see, when we crawl websites, right? If our different nodes reaching the URL, right? So it's not a good practice in crawling. I mean, if only one node is reaching out to a specific URL, dedicated node. So that's that's better from the being a nice perspective for the crawling, web crawling. So because now you are allocating a space for each node, so only one node at any point of time will reach out to any URL. So not multiple nodes.
So here, right, these hash spaces, like, is it how they will, like, they will keep their information, like they will know what is the hash space up within their topology, like the other nodes, and then because here there is no leader, right? It's kind of a leaderless protocol, correct?
Right. So there are two variants typically. The original protocol that came up, right? Card protocol. This was, if you guys remember,
What is
like
that?
long
Card?
time ago.
CRD.
CHORD.
Oh, card. Okay.
Right.
I see.
So that time, these distributed protocols were designed for like a BitTorrent, you know, like all these, you know, Nutella, right? Where you can have like millions of nodes, and there's no central control. Okay, so you have just like any, there is kind of they use some kind of epidemic protocol to join a cluster. So there, the information they maintain is they don't maintain the complete topology information, but just enough information to maintain this next set of neighbors, and then the next set of maintain the other set of neighbors. So the protocol designed such a way that any message can be sent to any other node in that topology in a log n number of steps. Okay, so meaning if you have like a 1,000 nodes, you know, you can reach in three steps, 3 hops, right? So
basically you try to identify, if you do not get within that range, then you again slash it, right? You don't go further, kind of.
Correct. So what they call every node basically maintains a table, and it and the table, the way it maintains the table is for this range you go to this next hop. So it has all the range, it has the next hop, and you only maintain log n. You don't
in the
maintain
sorting,
all
right? It will be in the sorted order, the table. Then you
Correct.
get a hash key. Then you look up, either you have to discard half of the information because you know, right?
Exactly. So you don't know the exact node, because this is with these there can be millions of nodes, right? So you don't maintain all the nodes in the card protocol. You only maintain log n nodes, kind of next hops to reach all the search space. You send to the next hop. Next hop looks it up. It looks it stable again, right? It sends the next hop like that until you reach the final destination. But once you read this, once you, this is designed such a way that at worst case, you need to do log n jumps to reach the real node that is responsible for that specific hash. Okay, so that's one protocol that's completely distributed, no leader. It's a leaderless protocol. So that's one way. But then you have this Cassandra and others use a variation of that protocol. They don't use card completely, but they just constraint hashing. What they do basically is that they it's also leaderless, but the distribution can happen. The distribution of which hash response or what node can be happen in a kind of a centralized way, because with something like Cassandra, you're not talking of millions of nodes, correct? There are only like a small set of nodes, maybe in hundreds, right? So for that you can maintain the full topology, meaning like if you have 100 nodes in the cluster, you can exactly maintain, okay, this node responsible for this hash range, right? You can maintain 100 entries, and then when the request comes, you exactly know for this range you need to go to this node. Okay, so that's O of 1. It's not O of log n. Like card, you need O of log n jumps, but in Cassandra and in Dynamo, basically they are all O of 1. You can jump to this node in O of 1 because you maintain the full topology information.
That also can be done in a a master node, right? Which will keep the information, and then it can look up and send to the appropriate server, right?
Yeah, I mean, you can use master architecture, but these typically are done completely in a leaderless way. What you could do is you could, let's say, because they use kind of an epidemic protocol to find all the nodes in the cluster, and it's called membership, right? They know all the nodes, and let's say the first node comes up, right? It knows this is the only node in the system. It finds out, and then it says, like, I'm responsible for the whole range, right? Let's say another node comes up, second node now, right? So now they only know two node, correct? And then it can pick up, oh, the previous node responsible for the full range. Now I can only pick for half, right? So as nodes are joining, they can know all existing nodes, and because through this membership protocol, they will keep exchanging information periodically. Hey, this is my node number. This is my range I'm responsible for, right? And then when the new node comes up, it can pick another range, or basically it can tell, okay, previous node is responsible for these ranges. Within that, it can pick some random ranges that it's going to take up, and it's going to tell, like, I'm responsible for this node. Through the membership program, it announces, and then everybody adjusts their table. So you can do this in a complete distributed way also, or you can do with a centralized control. Both are possible.
Right,
I
right.
think the
Is it the
central.
gossip protocol? You mean like
What is it?
gossip protocol, right?
Yeah,
Like
exactly,
you have.
exactly. Yeah, gossip protocol, correct. So
Gospel
this is
protocol maybe just tell everybody that the information I know, and I
Yeah,
think that topological, yeah, the
yeah.
structure.
that's a leader
Gossip
list,
protocol
right?
is for membership,
Everybody.
right?
Yeah,
It is for membership. You're saying I'm part of this group now, and then you will make you also make sure that if some node dies, right, that node will be removed. All of that. If new node joins, everybody is aware of the new node, right? And they can also exchange some information like the hash and the others. So it's maintaining all the membership and some additional information. That's what is gossip protocol for. New node joins or some node dies. All of that is maintained is because membership protocol.
I see. Yeah, I think the gossip protocol may tell everybody, every node that the distribution, the hash range distributed
Right.
of this system. Yeah, because
Correct.
I was trying to ask how to decide how those nodes know that what range it responsible for. But it seems that gossip can handle this.
Yeah, you basically, I mean, again, right? First node picks all the range, and after that, when a new node comes, they can look up the information. We can write such that these hashes are distributed, picked randomly,
Mm.
right? So that's how we ensure random kind of uniform distribution.
Yeah. So, does the Cassandra or DynamoDB use this way to handle? Let me see.
Yeah. They use constraint hashing. They use
Okay.
leaderless. There is no center leader.
Yeah, I know that at least the Cassandra and Dynamo, they don't have the leader for the whole system, and they use
Correct.
the gossip. Yeah.
Correct. There is
Okay.
gossip. And
Makes sense.
Google Bigtable, HBase, they use the like single leader. There is a one single leader, so they use master slave relationship.
Yeah, because
But
a single leader is easy to design, but it's hard to scale. That's my understand.
yeah, that's true. But the leader there, it's not in the data path. It's only control path. So and they have basically a fallback, a failover leader. So
Mm.
I mean, yeah, it's not that bad. I mean, I mean, they're able to manage.
Mm.
So because they have like
and
a
whenever you say the hash, right, is it something you mean either MD5 or
right, correct,
SHA-1 kind of?
correct. Yeah, SHA, yeah, HMAC. So yeah, there are some bunch of algorithms to
Okay.
calculate digest.
Yeah,
It's
yeah,
basically a digest, right? So
yeah.
the goal is that you give any random string of a random sequence of bytes, it gives you a fixed length value, right? And
Correct.
such that no random string will have a same hash.
Yeah, I think in this
Right.
case
Yeah,
we
with
have.
very lower probability.
Right.
Yeah,
Very.
my
I mean,
understand.
it's not impossible, but it's like near zero.
Yeah, my understanding of the hash there here, we have two purposes. One is to make sure it's a one-way hashing, so we cannot guess the original data. So that's why we
Right.
have the SHA and empty file. And another thing is that have the better distribution. And I remember the DynamoDB, sorry, the Cassandra have the different approach of hashing the key, some murmur, I think. Is it? Let me see.
There is specific hashing algorithm.
Yeah, that. Yeah, let me see.
I think
Yeah,
Murmur
so
3, right?
are you talking Merkle trees?
No,
Murmur 3.
Murmur tree. Okay.
Murmur
maybe
has,
this.
yeah.
Yeah, this one. Because I think that this one is used by I can't remember, maybe Cassandra or Dynamo, some database using this algorithm.
How do you
That's,
spell it? Murmur. Let me see.
Murmur has. Yeah.
yeah, this
So
one.
what's the property of that? Is it uniform distribution? That's what you need here in this case, right? This is not like a, yeah. It's we're not looking for a hash that where you cannot get back the original string. That's not the main objective here. The main objective
Yeah.
here is like uniform distribute.
That's right.
Yeah, one-way hashing we don't need here, right?
Right.
That's basically for the passwords and other things. But here, how to make sure, let's say that if we got a million
Here.
URLs, if they are falling in one bucket.
Right. Exactly. Exactly. That's
So
not good. Yeah.
how the hash can, if see the more ranges, yeah, I mean, I'm not sure, right? Because the hash function should be smart enough. It's kind of okay. I get 10 requests, right? Now I calculated 9 requests I distributed. Now I'm getting 20 requests, right? It's kind of the distribution of, right, like how uniformly you are doing based on your past values, right?
Right.
And
Right. Yeah.
also we need to know what is the total number of nodes somewhere, right?
That's
I mean,
handled by the
yeah.
gossip.
Yeah. That's where you need gossip. And the gossip basically, it maintains, every node maintains the full topology information through gossip. They keep sending their periodic heartbeats to everybody, and they all know from those heartbeats who are all the members, the complete list of members in the topology.
Yeah, that's right. I think this is using the gossip, we will have basically have the information shared by all the nodes, including
Correct.
the range of hash and also
Correct.
the
Correct.
number of nodes.
Correct. Exactly. They can do that. And not just that, like Dynamo and Cassandra also, like you could use this ring, right? Ring topology. Like for example, the way Cassandra replicates, right? Let's say this node here, let's say node 4, right? So the data that's being written to node 4 is also replicated at 3 and 2. Okay, so replication factor is 3. So that way, if this node number 4 dies, right, the 3 and 2 also have copies. So the fault tolerance also is done that way. So replication and is the previous the data is replicated in the previous 2 nodes, so that data is replicated. Now you're not going to lose data.
Yeah, that's I remember that.
Right.
This is a Dynamo's design that have the next couple of them have the data. But I think, let me see. Yeah, that's right. Dynamo and Cassandra have the virtual node.
Correct.
Yeah, there's not multiple nodes. Place can
So what
point
is
to a
that virtual node actually? Yeah, I have seen that actually.
So virtual node meaning, so each node, right? So if let's say each node is just a server, assuming each server here, if it's responsible for the certain range, right? So it means there's just one-to-one mapping, right? It means like let's say you have 1 1 1 1 2 2 2 2. So this whole server is responsible for that. Instead, what you could do is the entire physical node, let's say you can split into like 4 nodes, virtual nodes, and each of these 4 virtual nodes responsible for different hash range, so that even there's one physical server in this ring, there can be one virtual node here, one here, one here. All of them can map to same server.
Yeah, I think that's a distributed data.
Concept.
Yeah, that's
So will they use their same? It's kind of virtual host, right?
You're right. So it's one server. It can have same IP address, but in the protocol, right? They may advertise as it's like running the
different
same instance of the
IPs.
protocol. Yeah, within the gossip protocol, they may maintain different member ID, right? And so they don't really care about IP address really. So it's about like this is a member ID, and to reach this member, this is the IP address. And when the server gets that gossip, and it can distribute based on the node ID, right? So basically, each physical server running, like, let's say if the 4 virtual nodes, it running 4 instances of that that specific protocol. And and so that it can add itself at 4 places, in the ring. So that way, it's even more uniform distribution, right? This is one way to reduce hotspots now.
Yeah.
So
Back to the
so basically, the
physical.
more nodes you have in the ring, the more lesser hotspots you end up with, right? So that's why even with like let's say you have 2 nodes, you can create a lot of virtual nodes so that the load is distributed more uniformly.
Yeah, and they will share from the same physical resource. It's kind of a VM, right? You have
Yeah,
a
that's
physical VM, and then you created.
right, correct.
Right.
That's what it's called, virtual nodes, correct. Right. Yeah. It's basically in one server you're running 4 VMs, right? Each VM is a node, is a virtual node basically, right? So it's also that's the virtual node concept.
And this could be container also. We don't know.
Right. Correct. Yeah, it can be done.
You can spin up multiple container with the
right.
nodes, right? What you need is basically one address space, right? From the physical.
Right. Yeah. This is one of the technique they use. And then whenever every time you write something, then this is basically because leaderless they use quorums, right? So total number of there's a read acknowledge, write acknowledge. The total read plus write acknowledge should be greater than the total number of nodes, right? So that concept comes into picture. And Dynamo, they want a very high write throughput. So that's why in Dynamo they use something called read repair. Read repair meaning if a node cannot, let's say this node is down, let's say this node is supposed to store, it is down, right? So if a node receives, one node receives and randomly, and it knows number 4 is dead, the received node basically it's responsible. It writes local database and is responsible to send it to the other node after it comes back.
So node 3 is down.
Right.
And the data will be handled by node 4. Is it correct?
Right. And it's basically it has to write until if that node is down, then it has to no, sorry, I'm sorry, that's the right path. I mean, if when the write is received, if one of the node is if one of the node is down, the previous node is responsible for that, and until this node comes back, it has to it will store locally and then replicate after the node comes back. That's the right path, right logic.
Yeah. Anyway,
does it follow the memtable concept, Dynamo?
Yeah.
Like LSM trees?
Yeah, I think both Dynamo and I'm not sure Dynamo. Kasana definitely does the mem tables.
Yeah.
What's a mem table here?
Mem table is it's a different concept. That's for so even big table uses that. So basically, so all the databases, right? The way you have database is basically is that you can imagine, like, if you take any database, right, like SQL databases, they use B trees for implementation, right? So on the actual block storage, right, there are pages, right? And then each page maps to certain a chunk of data that goes in there in the table, right? So then all the information is how to reach a specific page to write, right, is what B trees do, right? B trees kind of a hierarchical indexing, right? So they use B trees.
Okay.
So that structure is good for random reads and random writes. You want to update a specific field in the database, that B tree structure is good because you are in few steps you directly know which block in the actual storage device, you need to reach, and then you can update that block, right? But they're not so good for write throughput. If you want to do many writes, they're not good. So for high write throughputs, what they do, something called
Append.
table. Yeah, they do append only logic. So all the writes, right? So they're basically appended. There will be a in-memory data structure, right? A sorted, where all the keys you are writing, they are being appended in a sorted order. And once that in memory, so every write goes to in memory first. Okay, and that's called a mem table, basically mem table. And and it's also called SS table, sorted string table, because that table is maintained in a sorted order by keys, right? You just
There's actually two things in the disk. One is SS table, that is for permanent, and there's a append only thing that is for current write.
Correct.
And write ahead log, actually. Wow.
Yeah,
you mean to say that? Yeah.
Because
what will happen if your memory crashes, right? Think about these two, right? You are writing 100 millions of record, and you haven't flushed to the database. The durability doesn't make sense, right? I think
so the write ahead log is used by all the systems, whether it is
correct.
SQL. The idea is that before you go and actually start trying to write to your database, you write in a file first. It's
append
basically
only,
an append,
right?
keep appending, right? Append only log.
Correct.
So that even if you in the middle of trying to write to your database, right, something crashes, happens, you come back up, and then oh, I was in the middle of writing. You look at the log and say, okay, I was writing this specific entry, and then you can make sure that you don't miss that. So that write ahead logs used in all the systems, right?
Yeah, I think the most of the files on the SQL database, SQL Server database using the write ahead something.
Yes, yeah. SQL, you just know SQL. Everybody is
NoSQL also, yeah.
Everybody is write ahead log. Yeah. All of them is write ahead log. Correct. So, but in this SS table, what is it? LSM log structured messages, right? So basically, it's like it's just like append only log of all the messages. But first, you append in a sorted order in your memory table, and once memory table goes certain length, you go and dump it in a file. Okay, and then then you keep writing, and if that file also grows big, you again actually the file doesn't really grow big. So first it goes in the memory table. From there you write your file. So you have one file on memory table now, right? Now let's say you have more writes coming in, your memory table full again, certain length. You go and write to that to another file. Okay, so you keep writing to files. So when the read comes, you first look into your memory table. Then you go and search memory tables. The files. If you don't find in your memory table, and you go on and look on this the files, the SS table files where you store in the memory. In the storage. And you do one by you first go read the most recent file, then go to the next recent, next, like that. And then
have to be in the reverse order.
Correct, reverse order. And then and at certain time there could be garbage collector. They could actually merge the files together to make even bigger files to remove duplicates. So
basically, if you have some data which is older,
right,
then it's kind of going to take your read path also going to take longer time, isn't it?
Absolutely. So this MM table, this structure, this MM table, SS table, mainly for very high throughput, very high write throughput. If you want to write a very high, if you want a very high write throughput, so that's why SS table and these things are good. If you want to have a
read throughput,
I think like Cassandra and the recent versions, they changed their implementation. I don't remember the details. I think they went slightly different path. They started from SS table, but they went slightly different path to improve the read throughput.
What the problem they find? What the problem they try to resolve?
the read throughput is not so great in this method, because
That's right.
right. So if you're reading most recent keys, right, it's fine. You may find a hit in the memory. It's very fast, right? But like if you're trying to read word values, they can be like in like number 10 file, number 100 file. They can be deep, so you need to keep searching, right?
Yeah, you can't make everybody happy.
Right. But they do use something called Bloom filters to quickly check. So you obviously don't go and check every thing in each file. They use something called Bloom filters. They're basically multi-way hash tables. You can determine if something whether if something is not in that specific file, you can find you can find whether it's present or not. It's called probabilistic find, right?
Bloom filter can see if a certain key
right
not exist in the file, in the table, but it cannot. I think that's a limitation.
Right. So yeah, it's I mean it's it's like checking membership whether the key present in that file or not, right?
Yeah, you cannot guarantee that the key exists in the table, because you may find it's a hit, but it may be a false hit.
False, yeah. So there will be no false negatives. There are only false positives, right? But because there are no false negatives, you may most likely eliminate a lot of. You don't have to look into many files.
Yeah,
you may still have to look into some files because they're false positive possible. Meaning even if it's not there, the Bloom filter says it is there. It is possible.
That's not the perfect solution, but a very good solution.
I think false negative means it will be a problem, right? If it is there and it is saying it is not
there. Then that's exactly. There are two criteria. There is a correctness criteria, and there is like an optimal criteria, right? Correctness has to be followed. Meaning like if it is there, you should not say it's not there. Then it means your read is going to the read is going to fail, or you're going to return a very old value, not a recent value, right? You will not guarantee freshness. So that's a correctness. But if you are saying if it is not there, if you say it's there, you will go and search anyway, and you will not actually find it. You're just, it means you just it just like read throughput will not be great for that key, but however you will not return a wrong result. So these are all kind of probabilistic structures, but the way they define is such that there will be few false negatives. So that's why they're defined that way, so that you don't have to search every file. You will end up only searching very few files.
Also, the file is the sorted, right? It is. Right. It's not a linear scan, correct?
It's not. Even if you don't, even if your Bloom filter says it is there and in reality it's not there, it's still a sorted search. It's still a sorted search.
So then how you decide which way to go? I don't know.
I think we need to dig up the code.
Yeah.
But this thing, I think this thing, not only the Cassandra, any local database should have this feature. Like
the Bloom filter.
Maybe Bloom filter and the local high table, because something like the RocksDB, I'm not sure how RocksDB handles this, but this is pure local thing.
Yeah, I mean, I think if you're talking about like a regular SQL databases, right, which they use basically B trees, straightforward. They use B trees, just hierarchical trees, where your table data is mapped into a bunch of pages which reside in some physical blocks, right? And then you traverse your B tree. I think in the worst case, B tree traversal is I think like what, like 16 steps, something like that.
Yeah.
So they're very deterministic.
It's very shallow actually.
Right, very shallow.
Correct.
Yeah, it's a very shallow.
And that's what, right? The reads will be much faster because the keys will be keep on extending, right?
Right.
If you based on the indexing structure of your table.
Right. Yeah. So
I think originally the write is very slow because it needs to reconstruct the access table. So this is a problem. This is a problem originally people want to resolve. Right. Then the write becomes faster and read becomes slower.
Right. Yeah, so correct, and that's why I mean it's all about use cases, right? It's all about, for
I
example,
don't know why they are not merging actually. For the storage, you do the indexing, right? B-tree, and you maintain the so that you will have a best of the both world, right?
yeah, but anytime you're creating two copies, right, there's always a consistency problem will
Yeah.
arise, right? So that's there. I mean, that's why like this table is good for write throughput. So that's why Dynamo choose, because they want a very high read throughput. They don't want any in their that DynamoDB is primarily used for all their like e-commerce applications, right? They don't want to lose any writes. They want the highest possible throughput, write throughput.
And another thing about DynamoDB is that they can handle the conflict resolving. So if
yeah,
the two
so
things
correct.
writing the same,
So it's correct. So basically, it's everything is kind of versioned. All the writes are versioned. So at the read time, right? At the read time, so because write quorum is set to 1, meaning one, even if you write to one node, you are fine. But read time, you are going to read from multiple nodes, right? And if these multiple nodes, one has old data and other one has new data, right? Then the read repeats, meaning it's called read repeat. So meaning the read time, whichever node has the old data, so that's going to be overwritten by newer data. Because each value is version. It's like a snapshot. They version each write, and they use read repair. So that way,
yeah, looks like on the Amazon Prime Day, there was an article yesterday.
Yeah.
In DynamoDB, 80 million requests per second.
Wow. Okay.
And it is 16.4 trillion calls to the DynamoDB API. I can share the link actually, which AWS published their Prime Day.
That's amazing. Yeah, I mean that's why they need that write throughput. It's
I mean 80 million requests per second is I don't know. Yeah.
Even consider how many nodes, how many machines they have. That's still a very high number.
Yeah, but I mean the limit talking about, I think it's not just scale out by adding more nodes, but from each node they need absolute best performance. We're talking about that much throughput, right? Yeah, so that's why if the all the design decision is all about, for Dynamo, it's all write throughput, and then they use read repair and the reading time, because each read from multiple nodes, right? Each read actually is not just read from one node. Data is so basically each data is persisted on multiple nodes, right? When we saw this ring, in this ring, each data is on multiple nodes. So at the time of read, the data will be read from multiple nodes, and then if the reading time, this has like 3 nodes, two different versions, and then you actually get the most recent data, and then at that call also will basically push their more recent value to other nodes which has old data. That's called read repair. So they do that on the read path.
But that might be taking some time on the consensus, right? If you are adding more and more nodes, then your ratio will be increasing, right? Your consensus will be okay.
Okay. I think today actually, it's pretty long. It's a long session, a very good session.
Yeah.
Talking about the database, and I think we can have a stop here about the web crawling, because we are clear about what to doing. So I would like to invite you guys to think about what we are going to talk next time. What kind of topic do you think is interesting for you?
So have you guys think about designing the status page? And I know I don't know about, like, right, statuspage.io and
status page.
Yeah, so I mean it's kind of a, I'm not sure if this is kind of a mainstream design question. Like, let's say that you are Pinterest, right? Then there, I mean, there are companies are there who actually design the the status page, and then whenever your service is down, then it will be updated on the status page.
That's a monitor.
The service monitoring.
I think
It's
service
kind
monitoring.
of, but I mean, yeah, I mean, it's okay. I was just thinking, right? Because nowadays the designs could be from any directions, right? Like, unknown topics will be more challenging to think and come up with the solutions, kind of thing, right? Yeah, may not be for next week. Maybe that could be
Right.
lack
Yeah.
of.
I think we need to try to be creative and pick something that's not mainstream. I agree on that.
Yeah.
Yeah. The last time we have the monitor, and we have the web crawling, and there could be other things like actually I have some list of the topic we can. There are only several topics we usually talk, and I don't want to have the similar topic.
Right.
What do we have here? Amazon
has this these mail locations, correct? Like if you don't, if they can deliver you to, they have locations where you can pick up from there, correct?
Location?
Mm-hmm.
Yeah. So Amazon,
like the store, Whole Food, those kind of things, right?
Yeah. So they can basically, they have locations. Yeah, correct. You're right. Sorry. It's called Amazon Locker.
Okay.
I think that's an interesting problem. There is two aspects to it. Design Amazon Locker.
That's an object storage thing, and it's that's a Wednesday thing.
Yeah. So basically, how do you maintain all this locker information, geographically distributed, right? How do you map? Each locker can have a different size, right? Small, large, medium. And these have pin codes, right? These lockers have pin codes. When the customer orders and selects a locker, then they need to get a pin. Only they can open. After they open, they lock it back. Now it has to be locked. Others cannot open, right? And so there is a different flows. For the person who delivers the mail, they need to open, put the mail there, and for the actual customer, they need to get a key to open. So there are different dimensions to it, right? I think this is when
this is more like an object storage to me. But let me see what. Yeah, there's location topic, and there is this time there's more like MapReduce style thing, and yeah, I'm from one of the training thing. Web crawler.
So did we discuss anything about like designing like anything system, right? Like a distributed cache or a unique ID. It's kind of another bucket, right? Which is not a business driven kind of a. I mean, I think it's similar to
building some primitives, right? Some primitive basic capability.
Yeah, I think that's that's more like a database related thing. Design a database.
Yeah, like designing something distributed cache or
I think design distributed cache. I think we discussed last time, right? Last Saturday or before that, there was the topic designing distributed cache. Yeah, it was in the mock interview.
Okay.
Oh, I see. Okay.
Design a cache. I think we can talk about design a cache. What kind of cache? Distributed cache.
Yeah, I mean, in memory cache. Yeah, there will be challenges, right? Because it's the same way as because Redis is kind of, they have both the world, right? They have in memory also they need to, plus to the disk, right? It's kind of interesting domain, and then how you need to SAD against, right, distributed, because it's the same exactly like the database constraint you will face, right?
Yeah. Maybe we can design the real concrete database next time. What do you guys think?
What is that? Real?
Yeah, some dynamo style database. Let's we get together and design one. Yeah, it's all about
Yeah, I
the
think-
knowledge.
Yeah, so a kind of NoSQL database.
Yeah. Let me
Yeah.
think about it. Or maybe you guys can
Yeah, you can.
put some comment in the.
Yeah, Discord, right? Yeah.
Yeah.
We could do
Yeah.
that probably. Yeah.
Okay.
Okay.
Yeah. Hope to see you guys next time.
Thank you
Thank you.
guys. See you next time.
Thank you. Bye.
Thank you.